Hello friends, continuing with the chapter of current electricity, today we come to the third topic as per mind map, which is series parallel combination of resistances. What is the topic today? Today's topic is series parallel combination of resistances. We take up point by point. First, need of combination of resistances. That is why we need combination of resistances. Now, in order to manipulate the desired value of resistance, resistances are combined either in series or parallel combination or simultaneously in both ways. I repeat, in order to manipulate the desired value of resistance, resistances are combined either in series or in parallel combination or simultaneously in both ways. Okay. Now second, series combination of resistances. That is how we connect resistances in series. When same electric current flows through each resistor, then resistances are said to be connected in series. That is, you look at a diagram, resistances R1, R2, R3, Rn are connected end to end alternately. So we say these resistances are connected in series and the same current will flow through these resistances. Okay. I repeat, when same electric current flows through each resistance, then resistances are said to be connected in series. Now, law of series combination of resistances. A statement of law of series combination of resistances. When number of resistors are connected in series, then the equivalent resistance of the combination is equal to the algebraic sum of all the resistances of the combination. I repeat, when number of resistors are connected in series, then the equivalent resistance of the combination is equal to the algebraic sum of all the resistances of the combination. Now look at the diagram. There are n resistors which are connected in series, and the combination is further connected across a source of EMF B dash. Now, mathematical expression. Suppose n resistors R1, R2, R3, Rn, R1, R2, R3, Rn are connected in series. Then the equivalent resistance of the combination is given by the expression R equivalent is equal to R1 plus R2 plus R3 plus so on up to Rn. I repeat, suppose n resistors R1, R2, R3, Rn are connected in series, then the equivalent resistance of the combination is given by the expression R equivalent is equal to R1 plus R2 plus R3 plus so on up to Rn. Okay. B. Proof. Let us develop physical situation first. Consider n resistors R1, R2, R3, so on Rn connected in series. The combination is further connected across a source of EMF B dash having terminal PD as V volts as shown in diagram. Now second step is current through each resistor is same and let it be I, and PD across each resistor would be different. The third step, we have to apply Ohm's law for calculation of PDs across each resistor. That is, we have to use the formula V is equal to IR. Let V1, V2, V3 and so on Vn B. The PDs developed across R1, R2, R3 and so on up to Rn respectively. Then V1 is equal to IR1, V2 is equal to IR2, V3 is equal to IR3 and so on. Vn is equal to IRn. Now adding, we get V1 plus V2 plus V3 plus so on Vn is equal to IR1 plus IR2 plus IR3 plus so on plus IRn, or V is equal to I common R1 plus R2 plus R3 plus so on plus Rn, where V is equal to V1 plus V2 plus V3 plus so on Vn. And finally we write V is equal to I into R equivalent, where R equivalent is equal to R1 plus R2 plus R3 plus so on plus Rn. Now fourth, equivalent circuit. Equivalent circuit can be drawn as shown, where R equivalent is equal to R1 plus R2 plus R3 plus so on plus Rn, and is the total resistance of series combination. Hence R equivalent is equal to R1 plus R2 plus R3 plus so on up to Rn. Now fifth step is discussion. Now R equivalent is higher than the highest in series combination. For example, consider three resistances of 100 ohm, 220 ohm and 330 ohm connected in series. Then their R equivalent will be 100 ohm plus 220 ohm plus 330 ohm, and it will be equal to 650 ohm, and 650 ohm is greater than 330 ohm and is higher than the highest in the combination. Highest in the combination is 330 ohm and R equivalent is 650 ohm. Now assignment 3.3, question number 1. VI graph of two resistors and their series combinations are as shown. Which graph represents series combination and why? Now question number 2. IV graph of two resistors and their series combination are as shown. Which graph represents series combination and why? Our third part of the topic is parallel combination of resistances. Now how resistances are connected in parallel, let us understand. When same potential difference is applied across each resistance, then the resistors are said to be connected in parallel. I repeat, when same potential difference is applied across each resistance, then the resistors are said to be connected in parallel. Now look at the diagram. There are n resistors R1, R2, R3, Rn connected in parallel, and the combination is connected across A, B. And across AB we have connected a source of EMF having terminal PD as V volts. Now since all resistors are connected across A and B and battery is also connected across A and B, therefore V is applied across each resistor. Okay, so we say these n resistors are connected in parallel because PD is same across each resistor. A. Law of parallel combination of resistances. When number of resistors are connected in parallel, then the reciprocal of equivalent resistance of the combination is equal to the algebraic sum of the reciprocals of all the resistances of the combination. I repeat, when number of resistors are connected in parallel, then the reciprocal of equivalent resistance of the combination is equal to the algebraic sum of the reciprocals of all the resistances of the combination. Now mathematical expression. Suppose n resistors R1, R2, R3, so on, Rn are connected in parallel, then the equivalent resistance of the combination is given by the expression 1 by R equivalent is equal to 1 by R1 plus 1 by R2 plus 1 by R3 plus so on up to 1 by Rn. So this is mathematical expression for law of parallel combination of resistors. So when we say R equivalent, it means it is the total resistance between A and B. Now B, proof of the law of parallel combination of resistance. First we develop physical situation. Consider n resistors R1, R2, R3, so on, Rn connected in parallel. The combination is further connected across a source of EMF having PD as V volts as shown in diagram. Now second point, same PD across each resistor. Now since potential difference across each resistance is same, therefore current through each resistor would be different. Let it be I1, I2, I3, so on, In respectively through each resistor R1, R2, R3, so on up to Rn. Now 3, we are to calculate current through each resistor, and it can be calculated by using Ohm's law. V is equal to IR. From this equation we have I is equal to V by R. Therefore current through resistor R1, say I1 is equal to V by R1, through R2 say I2 is equal to V by R2, and through R3 say I3 is equal to V by R3, and so on, so forth, and through resistor Rn say In is equal to V by Rn. Now adding, we get I1 plus I2 plus I3 plus so on plus In is equal to V by R1 plus V by R2 plus V by R3 plus so on V by Rn, or I is equal to V by R1 plus V by R2 plus V by R3 plus so on V by Rn, where I is equal to I1 plus I2 plus I3 plus so on plus In, or we can write I is equal to V, we can take out V common, here V common, within bracket 1 by R1 plus 1 by R2 plus 1 by R3 plus so on 1 by Rn, or I by V is equal to 1 by R1 plus 1 by R2 plus 1 by R3 plus so on 1 by Rn, or we can write 1 by R equivalent is equal to 1 by R1 plus by 1 by R2 plus 1 by R3 plus so on plus 1 by Rn, where R equivalent is equal to V by I. Okay, because 1 by R equivalent is equal to I by V. Hence, reciprocal of equivalent resistance is equal to the algebraic sum of reciprocals of all the resistances in parallel combination. I repeat, reciprocal of equivalent resistance is equal to the algebraic sum of reciprocals of all the resistances connected in parallel combination. Okay. Now equivalent circuit of combination can be drawn as shown. Now look at the circuit. R equivalent is the equivalent resistance of the combination. I is the current flowing through the combination, and V is the potential difference applied across the combination, and then this constitutes the equivalent circuit. From here we have 1 by R equivalent is equal to 1 by R1 plus 1 by R2 plus 1 by R3 plus 1 by Rn. So this is the law of parallel combination of resistance, which states that the reciprocal of equivalent resistance of a parallel combination of resistors is equal to algebraic sum of the reciprocals of each resistor in the parallel combination. Okay. Fifth, discussion. First, equivalent resistance of the parallel combination is lower than the least in the combination. I repeat, equivalent resistance of the parallel combination is lower than the least in the combination. So you remember this point, because this point is going to help you in computing numerical problems for verification of results, etc. For example, consider three resistances of 100 ohm, 75 ohm and 25 ohm connected in parallel, and the combination is further connected across points A and B. Then equivalent resistance can be calculated using the formula as 1 by R equivalent is equal to 1 by 100 plus 1 by 50 plus 1 by 25, and it is equal to 1 plus 2 plus 4 divided by 100, because 100 is the LCM, and then when we simplify it, we get it equal to 7 by 100. Or taking reciprocals of left hand side and right hand side, we have R equivalent equal to 100 by 7, or it is equal to 14.43 ohms, which is less than 25 ohm, the least in the combination, because 25 ohm is least in the combination and the equivalent resistance is 14.43 ohm, which is less than 25 ohm. Hence, the equivalent resistance of the parallel combination is lower than the least in the combination. Okay. Assignment 3.3 continued. Question number 3. VI graph of two resistors and their parallel combination are as shown. Which graph represents series combination and why? Question number 4. IV graph of two resistors and their parallel combination are as shown. Which graph represents series combination and why? Assignment 3.3 continued. Question number 5. A student was asked to measure the value of two given resistors in lab. He had the following four observations: 3 ohm, 4 ohm, 12 ohm and 16 ohm. What are the values of individual resistors? So here I give you the hint. Use the information that in series combination the equivalent resistance is higher than the highest in the combination, and in parallel combination the equivalent resistance is lower than the least in the combination, and you will get the answer. Okay. Now second point of discussion. When only two resistances are connected in parallel, then how we calculate equivalent resistance? Now consider two resistors R1 and R2 connected in parallel. Then their equivalent resistance can be calculated from the expression 1 by R equivalent is equal to 1 by R1 plus 1 by R2. And taking LCM as R1, R2 in the denominator, then in the numerator we write R2 plus R1. And when we take the reciprocal of these left hand side and right hand side, we get R equivalent equal to R1 into R2 divided by R1 plus R2, or it is equal to product divided by sum. Thus, when only two resistors are connected in parallel, the equivalent resistance of the combination is equal to their product divided by their sum. Now for example, consider two resistances of 100 ohm and 50 ohm connected in parallel. Then their equivalent resistance is 100 into 50 divided by 100 plus 50, or it is equal to 5000 by 150, or it is equal to 100 by 3, or it is equal to 33.3 ohm. Now 33.3 ohm is lower than the least in the combination. It means least in the combination is 50 ohm. So the equivalent resistance is 33.3 ohm. It means our answer is correct. So this is how we can calculate directly the value of equivalent resistance of parallel combination of two resistances. Directly you write product divided by sum. That will give you the value of R equivalent. Third point of discussion, when two equal resistances are connected in parallel. How we calculate equivalent resistance. Now say there are two resistances R1 and R2 connected in parallel which are equal to R. Then their equivalent resistance 1 by R equivalent can be expressed as 1 by R plus 1 by R, or it is equal to 2 by R. And finally R equivalent is equal to R by 2. Thus, when two equal resistances are connected in parallel, the equivalent resistance of the combination becomes half of their individual values. Half of their individual values. So mark this point. When two equal resistors are connected in parallel, their equivalent resistance becomes half. For example, consider two resistances of 100 ohm and 100 ohm connected in parallel. Then their equivalent resistance will be 50 ohm. Okay, directly you can write 50 ohm, and if you are asked to calculate and then write the value, then you calculate 100 into 100 divided by 100 plus 100, it is equal to 10,000 by 200, or it is equal to 100 by 2, or it is equal to 50 ohm. So directly you can compute when two equal resistors are connected in parallel, then their equivalent resistance will be half. Now assignment 3.3 continued. Question number 6. Evaluate equivalent resistance of the following combinations. Here the first is the second, is the third. Answers are given alongside. This is the fourth. Now question number 7. A straight wire of resistance 4R is bent to form a circle. Calculate resistance across diameter of the circle. Question number 8. You are given n resistors, each of resistance small r. These are first connected to get minimum possible resistance. In the second case, these are again connected differently to get maximum possible resistance. Compute the ratio between minimum and maximum value of resistance so obtained. Now this is all about series and parallel combination of resistances. On the basis of the text that you have learned, you solve these numerical problems. Next time we will take up fourth topic of this chapter according to mind map, that is Joule's law of heating. Till then, goodbye.